So in this lecture, we'll study how electromagnetic wave propagate in a lossless medium such as air. The relevant section in your book are section 10.3 and section 10.4. So we know that Maxwell equation can be used to predict any electromagnetic phenomena. So we will start with the Maxwell equation and we'll derive the wave equation in a lossless medium. The objective is that we want to see how electromagnetic wave propagate in a lossless media like free space. Then we will try to solve this wave equation using an assumption or approximation of uniform plane wave. And then we will study the basic properties of electromagnetic plane wave in a lossless media. So these are the four Maxwell equations, which are the basis of any electromagnetic phenomena. We have two divergence equations and two curl equations. So Maxwell published a landmark paper back in 1865 with title A Dynamic Theory of Electromagnetic Field, in which he demonstrated that light is the same phenomena as the electromagnetic wave and electromagnetic field are coupled together. So our objective in today's lecture is to see how Maxwell equation can be used to predict the EM wave in lossless media like free space. So we have already studied Maxwell equation. So these are the Maxwell equation in time domain. So this is the Faraday's law. Then we have Ampere's law with this displacement current term. Then we have Gauss law of electric field. And lastly, we have the Gauss law for magnetic field. So we have four equations in total, two curl equation and two divergence equations. Now we are considering the waves in free space or in a lossless media. So in free space, there's no sources. So we will assume that we have a source free region. So this term will become 0. And because J is equal to sigma E, this is the conduction current term. So this sigma is 0 for lossless media. So this J term will also be cancelled. So these four equations will become simplified, and for source free and lossless media such as free space, the Maxwell equation will become like this. So this J term becomes 0 and this rho V term also becomes 0. Please note that these equations predict a wave phenomena, because if you look closely at these two equations, for example, these two curl equations, it says that a changing magnetic field produce a circulating electric field. So if we have a changing magnetic field, it will produce a circulating or curling electric field. Now, a changing electric field in turn will produce a circulating or curling magnetic field. Similarly, a changing magnetic field will again produce a circulating electric field, and this phenomena of changing electric field and changing magnetic field will go forever. So this is actually the phenomena of wave. So for time varying electric and magnetic field, they are coupled together. Each one changing with time produce the other one. So you can see this by closely observing these two curl equations. So we can also write this Maxwell equation in phasor form. So these are Maxwell equation for source free and lossless media. So for writing this in phasor form, all you have to do is to replace this partial t term with j omega. So, but differentiation in time domain is equivalent to multiplication in the phasor of frequency domain. So if we do so, we'll get these phasor equation. So please note that the notation when I am using this E of t, this is actually time domain signal, instantaneous signal, which is equivalent to a function of x, y, z, and time, a shortened notation of this signal. And when I am not using this time domain symbol, that is, this is shorthand notation of phasor domain signal, which will be only a function of x, y, and z only. So these are all the variables in these expression are vector phasor or uh, vector field in instantaneous. So these are instantaneous vector field, and these are the phasor vectors. I also use the constitutive relation here, that B is equal to mu h here, and for D I have used D is equal to epsilon E. So these were my 4 Maxwell equation in the phasor form. Now the question is, if we want to find, let's say, electric field in a lossless medium, how can we use Maxwell equation to find the electric field in a lossless medium? What we need to do is to derive vector wave equation. So if you consider the first two equations, first two Carl equation in the phasor form, if you closely observe these two equations, we have actually how many unknowns, how many equations and how many unknowns are there?
Two unknowns.
Two unknown and two equations. Let's call this equation 1 and let's call this equation 2. And we have electric field and magnetic field both appearing in first equation. Similarly, in second equation, we also have magnetic field and electric field. So we call these type of equation, we say that these are coupled partial differential equations. So first step is usually that we want to decouple them. We want to express them as a single variable. So if we want to, let's say, find the electric field, then we want to express them as a single variable of, let's say, E field. So the usual step for doing this is that what we do is that we take the curl of first equations and substitute the second equation. So let's say if I take the curl of first equation, let's say curl of E will become minus j omega mu times curl of H. So I take the curl of first equation, this equation. Then this for here, for curl of H, I am substituting the second equation back in this equation. So if I substitute this, j omega mu times curl of H is j omega epsilon E. So this j square will minus 1 and minus plus. We have omega square mu epsilon E. So curl of E will become this thing. So now we have single variable E. So this is the usual step for deriving the vector wave equation. So what we do is we take the curl of first equation, then we substitute the second equation back, and then we define this omega square mu epsilon. It's a constant. We can define it as beta square. So then if we take the square root of this, we define that beta by definition is equal to omega mu epsilon square root. We call this the wave number or phase constant. Please note that this is the same thing we defined earlier, which was beta is equal to 2 pi lambda. Okay, so this we define this constant as beta. Then our equation will become, if I move this term to the left hand side, we can write this curl of E equal to minus beta square E equal to 0. Next, what we can do is that we can use a vector identity. So curl of a vector field is a vector identity which says that curl of a vector field is equal to gradient of a divergence of that vector field minus Laplacian of that vector field. So if I replace this curl of E with gradient or divergence of E minus Laplacian of E, I can write this term will replace this term with this here. So I'm using this vector identity. Now please note that this divergence of E. So the Gauss law of electric field, the Maxwell equation was divergence of D is equal to rho V. Divergence of D is equal to rho V. And because we are talking about the source free media, so this term will become 0. So divergence of D is equal to 0, and D is equal to epsilon E. Epsilon cannot be 0, so this means that divergence of E must be 0. So this term here is actually will become vanish. So this first term in a source free media or lossless media, this term first term will become 0. So we in the end we get this expression, that is Laplacian, vector Laplacian of E plus beta square E is equal to 0. So this equation is a partial differential equation, partial second order differential equation, a vector differential equation, and it has a name. This is called vector wave equation. So what we have done is that we have derived a vector wave equation. So this equation is known as vector wave equation, and another name for this equation is vector Helmholtz equation. So now if a question can be asked that if let's say I want to derive a vector wave equation for magnetic field, what step should I do? क्या करना चाहिए? We have derived the vector equation for E. If let's say I ask you to derive a vector wave equation for H field, what step you should follow? What you will do is that you will take the curl of this second equation and you will substitute this first equation back. So in this way, if you follow these steps, you will end up with vector wave equation for H field, and it has the same mathematical form, only E will be replaced with H. So please do it as a homework. So this you will get in the end this equation. So this has the same mathematical form as that of electric field. Okay, so next we have this vector wave equation. So please note that the Laplacian in vector Laplacian in rectangular coordinate system will have three components. We have AX component, AY component, as well as AZ component. So basically, this single equation is equivalent to how many equations? So this is a vector equation. This is equivalent to three scalar equation. So this actually, in fact, this equation is equal to these three scalar wave equation. So this equation, single equation, represent these three equations. So these three equation has same mathematical form. If you let's say solve one equation, the solution of other will be same. So for simplicity, what we can do is that let's assume that electric field in general have three components. Let's assume that electric field has only, for simplicity, it has only X component, and other component, let's say two component are 0 for the time being. So if we use this assumption, then that is we take only the X component, then this vector wave equation under that assumption will become a single wave equation. These two equations will be 0. We write this as del square Ex plus beta square Ex is equal to 0. This del square is basically scalar Laplacian. So this equation, this was our vector wave equation, and this equation is known as scalar wave equation, because here we have a vector sign, and we are dealing with scalar component, only one scalar component. So actually these three again, these three scalar equation, and we are choosing only one by using this assumption that electric field has only one component. So this is the scalar wave equation. We want to solve this scalar wave equation, and we want to find the electric field. The objective is to find the electric field in a lossless media or in free space. We will use a uniform plane wave approximation, which I explained in the previous lecture. So if we have a let's say have a radiating antenna, it will have a spherical wavefront, it will radiate spherical wavefront, but when the observer is far from the antenna, let's say this is a radiating mobile tower, and let's say you are here with your mobile phone, so you are actually very far from this mobile phone tower. So in terms of lambda, so locally you will experience a plane wave, and so we are talking about the plane wave solution, and we are also talking about the uniform plane wave. Uniform means that electric field magnitude is, if we take, let's say this as a plane, electric field magnitude is everywhere constant in this plane. Uniform mean constant. So we are let's consider that this plane here, let's consider this xy plane, and let's say assume that electric field, because we are taking the let's call this the x-axis and this is y-axis, and because we assume that electric field has only x component, so these red arrows are representing electric field, and we are assuming that electric field magnitude is constant, that it is uniform in this xy plane. So this is our uniform plane wave lying in the xy plane, and wave is actually traveling in the z direction. So this is our assumption that electric field is only x component, it is oriented in the x direction, and it is only a function of z. It is constant with it is or uniform with respect to x and y. So electric field, these are our assumptions. Electric field is polarized or oriented in the x direction. One assumption. Electric field is uniform in this xy plane. This means that the partial derivative with respect to x and y will be 0. So electric field is uniform in the xy plane, but it is traveling. We are talking about the traveling wave, so the wave will actually in 3 dimensions, it will be traveling in the z direction. So this is just one instant of time. Actually, wave will be a different instant of time. Wave will be traveling in the plus z direction. And third assumption is that wave will propagate in the z direction. So under these uniform plane wave approximation, we want to solve this our scalar wave equation. So this is our uniform plane wave assumption, and physically it look like this, that electric field lies in the xy plane. It is a function of only z, that is it is traveling in the wave is traveling in the z direction. So under this assumption, let's solve this scalar wave equation. So this Laplacian in Cartesian coordinates can be written as a partial square or partial x square ex partial square over partial y square ex plus partial square or partial z square ex. So this is actually this term expanded. And because we are using uniform plane wave assumption, electric field is only a function of z. So these first two derivative will become 0. So we will only left in this expression. Here I use the ordinary derivative. So when we use the ordinary derivative and when we use the partial derivative, कब use करते हैं जो partial derivative and कब ordinary derivative?
जब सर उसमें एक से ज्यादा वेरिएबल्स होते हैं और हमें सिर्फ एक वेरिएबल को डिफरेंशिएट करना तो
Yes.
पार्शियल
Let's say if electric field, let's say for sake of argument, is a function of two variables, and let's say we are taking derivative with respect to one variable. let's say partial x, then we use the partial derivative. On the other hand, if let's say electric field is a function of only single variable, then we don't use the partial derivative, simply use the ordinary derivative. So here, because x is a function of z only, so I can replace this partial derivative with this ordinary derivative. So this is actually a second order partial differential, ordinary partial differential equation. So you have studied this type of equation in mathematics. So you usually do is a form a characteristic equation corresponding to this equation, and then you find the roots of this equation. The final solution, I'm writing here the final solution of this second order ordinary differential equation. So Ex, which is actually a function of z, the solution of this equation is E naught exponential of minus j beta z. So this is the solution. So this solution is only valid for if a wave is traveling in the positive z direction. So because our wave is traveling in the plus z direction. Again, note that we have minus j beta z for wave traveling in the plus z direction. On the other hand, if let's say our assumption, let's say our original assumption was, let's say if wave is instead of positive traveling in the positive direction, if we have a wave which is traveling in the minus z direction, then solution will be look like this. Then we will replace instead of minus j beta, we have plus j beta z for wave in traveling in the minus z direction. And beta we have defined as a constant is equal to omega mu epsilon square root. So this is our solution of scalar wave operation in the frequency or phasor domain. So we started with the Maxwell equation in the phasor form. We derive a vector wave equation. Then we take the assumption that electric field has only x component, and under the plane wave assumption, we solve the scalar wave equation, and this is the final solution in the frequency or phasor domain. That Ex is equal to E naught exponential of minus j beta. How can I convert this phasor signal back into time domain? कैसे करेंगे जी? हम करते रहेंगे.
So real of Ex into e j omega t.
So all you have to do is to multiply this phasor Ex with exponential of j omega t and take the real part. So we take this phasor, multiply it with exponential of j omega t. There should be a plus here, and take the real part. So if you do so and use the Euler identity, we end up with electric field x component as a function of time, or E naught cosine omega t minus beta. So does this expression look familiar? ये किस की expression है? This is actually a what type of wave?
Positive z direction. Cosine.
It's a traveling wave moving in the positive z direction, because it's a function of both space and time, and minus z mean that is a traveling wave moving in the positive z direction. So just looking at this expression, you should immediately recognize that it's a traveling wave moving in the positive z direction. And from our discussion in the previous lecture, we said that the phase velocity of a traveling wave is u is equal to omega by beta. So we have defined omega beta here in this lecture as beta is equal to omega mu epsilon square root. So if you replace this beta with this omega mu epsilon, then this omega will be cancelled, and u will become 1 over mu epsilon square root. Please note that this means that velocity or phase velocity of our traveling wave only depend on the medium constitutive parameter. So it only depends on epsilon and mu. Now, if you calculate the velocity of wave for free space, so you can use this for epsilon naught, use 8.85 into 10 power minus 12 farad per meter, and for mu naught, use 4 pi into 10 power minus 7 Henry per meter. If you substitute this and multiply and square, take square root, and then the reciprocal, then u comes out to be 3 into 10 power 8, which is actually the c, or the speed of light. So this was the observation when Maxwell derived the wave equation back in 1865. So he calculated the velocity of the EM wave. So when it comes equal to 3 into 10 power 8 meter per second, then he declared that light and EM wave are one and same phenomenon. So in this way, we can see that because they both have same speed, so they must be the same phenomenon. So up till now, we have find the electric field in a lossless medium. We found that it is phasor solution in E naught exponential of minus j beta z, and in vector form it will be, you have to just multiply with this ax unit vector, you will get the electric field. Please note that we use the assumption that electric field has only one component, x component. Now we want to find the magnetic field corresponding to this phasor electric field. How can we do this? कैसे कर सकते हैं जो है? How can we find the magnetic field corresponding to electric field? इस कोर्स में हमने कुछ स्टडी की है ऐसी जो है? We can use the Maxwell equation. So if we use this, let's say Maxwell curl equation, curl of E is equal to minus j omega mu h. So if we are given E and we want to find h, so if I manipulate it like this, then the curl of E is mathematical given by this expression. Please note that electric field has only x component. So this y component and z component will become 0. And it is only a function of z. So this means that this y derivative and x derivative are 0. So we end up with only with, if you expand this, we get d by dz of ex. Now, if you replace this ex with this exponential naught E naught exponential of minus j beta z. So in the next step, Ex will remain as it is, and we get minus j beta here. So here j will be cancelled, and this minus sign will become plus. So we get beta over omega mu E naught exponential of minus j beta z times ay. So in next step, we can use the definition of beta here, that beta is equal to omega mu epsilon square root, then this omega will be cancelled. And if we take this mu inside this square root, we can take it inside by taking its square root, and this mu will be cancelled, and we have epsilon over mu square root. I can do one more step. If I take it a reciprocal here, that I can also write it E naught over mu over epsilon square root. So this expression here is the magnitude of magnetic field. Let's call this H naught. Please note that H naught, or magnitude of magnetic field, can be found if you are given this E naught. If you know the E naught or magnitude of electric field, all you have to do is to divide this with this square root of epsilon over mu square root. You immediately know the magnitude of magnetic field. And H naught is also a traveling wave in the plus z direction, but its direction is, electric field direction was in the x direction, but magnetic field direction is orthogonal to electric field. It comes out to be in y direction. So this is our H naught, and H, so magnetic field has only y component. So this is whole thing is Hy, and this is Ay unit vector. So H naught can be found from E naught by dividing it by, we are defining this a number eta, which is, we will see that it is called intrinsic impedance, mu or epsilon square root, by which is by definition mu or epsilon square root. So if you divide E naught by this eta, you find the magnitude of magnetic field. So this is our electric field, which is E naught exponential of minus j beta z in the x direction, And this is our magnetic field, which is H naught exponential of minus j beta z in the y direction. And this H naught can be found from E naught by dividing it by simply this eta, and eta is basically the ratio of E naught and H naught by definition. And this eta is called the intrinsic impedance of medium. What should be the unit of this eta? Unit क्या होनी चाहिए? Why it is we calling it intrinsic impedance? What is the unit of electric field? Can somebody tell me? What is the unit of electric field?
Volt per meter.
Volt per meter. And what is the unit of this H naught magnetic field?
Ampere per meter.
Ampere per meter. So this will be cancelled. We have at the end left with volt over ampere or volt over current. So what this thing is? What is the unit of this thing?
Ohms.
Ohm. So this is the impedance. That's why we are calling this intrinsic impedance. So its unit is ohm. And for free space, if you let's denote it free space intrinsic impedance by eta naught. So if you substitute value of epsilon naught and mu naught, you get a simple constant which is approximately equal to 377 ohm, which is also equal to 120 pi. So for it's a constant number for a free space. We sometime before we also calculated the velocity, which was equal to 1 by mu naught epsilon naught square root, which came equal to the speed of light, 3 into 10 power 8. So speed of light can also be calculated using constitutive parameter epsilon and mu naught, and intrinsic impedance can also be calculated using this constitutive parameter epsilon and mu naught. And please remember it's a constant. So here's the summary of today's lecture. So in frequency domain, electric field has only X component. So this red arrows are showing electric field is oriented in the X direction. And this E naught is in general can be a complex number. It can have a magnitude and phase. So if we have, let's say, some reference phase in the, let's say, in the cosine signal, then this phi will be some positive or negative number. And magnetic field, please note that magnetic field is given by this shown here by this blue arrows. It's oriented in the y direction, orthogonal to electric field direction, and direction of propagation is in the z direction, which is orthogonal to both electric field and magnetic field direction. So if you are given the electric field direction and magnetic field direction, and you are asked to find the direction of propagation, let's denote it with k. So all you can do is simply take E cross H. If you calculate this cross product, E cross H, you will find the direction of propagation of wave. And the magnitude of the magnetic field can simply found by dividing E naught by this intrinsic impedance eta. And in time domain, we can find the time domain signal by multiplying these two signals with exponential of j omega t and taking the real part. So we will have these two traveling waves in the time domain. So we have two traveling waves in the time domain. जी
सर आपने कहा था ना कि ई के तो डायरेक्शन ई की कॉम्पोनेंट्स तीनों में एक्स वाई और जी में और ऐसे ही एच में, तो अगर अब इनका आंसर क्रॉस प्रोडक्ट लेंगे तो वो
एक्स वाई जी में नहीं, हमने अभी अजम्पशन ली थी कि इलेक्ट्रिक फील्ड का सिर्फ एक कंपोनेंट है. बाद में हम इस अजम्पशन को मजीद देखेंगे कि उसका मतलब क्या होता है. We have taken that electric field has only one component. It is oriented in the x direction. ठीक है, जब स्केलर वेव इक्वेशन जो हमने की थी वो that was a scalar wave equation. It has only x component. ठीक है, हमने तीनों कंपोनेंट नहीं लिया, हम एक कंपोनेंट लिया.
जी जी सर, मैं समझ रहा हूँ सर, एक कंपोनेंट लिया था. इन केस अगर हम तीनों लेते तो फिर तो सर वो
डिफरेंट चीज है, वो उसमें और अभी का कांसेप्ट है वो अभी आपने नहीं पढ़े. वो पोलराइजेशन के कांसेप्ट हैं और वो चीजें जो है उसमें वेव फिर सर्कुलेट करती है, वो अभी लेटर ऑन कोर्स के लिए देखें. अभी फिलहाल ये चीजें समझ लीजिए. इलेक्ट्रिक फील्ड, if we have electric field oriented in the x direction, the magnetic field will be orthogonal in the y direction, and direction of propagation is orthogonal to both x and y. It will be in the z direction. So this is graphical representation, electric field is in the x direction and magnetic field will be in the y direction, and it is actually a traveling wave. I am showing it only at a 1 instant of time. It's just a snapshot at t is equal to t/4. In general, the wave will look like something like this. So we will have two waves, an electric field wave, let's say this yellow, and this blue wave is let's say magnetic wave. They are both orthogonal and they are moving in the z direction, and they are both are traveling waves. So this is just an instant. One snapshot at t is equal to t/4 of that traveling wave. So here are some observations. The first observation is that electric field is orthogonal to magnetic field. Electric field is oriented in the x direction and magnetic field is oriented in the y direction. So electric field is oriented in this direction and magnetic field oriented in this direction. Both are orthogonal to each other. Second observation is that electric and magnetic field are orthogonal to direction of propagation. So not only they are orthogonal to each other, they are also orthogonal to direction of propagation. So what type of wave is this electromagnetic wave? Longitudinal wave or transverse wave? Electric and magnetic field are orthogonal to direction of propagation. So they are constituting a transverse wave or a
Transverse
wave. So that's why we call them as a TM wave. So wave propagating in a free space or lossless medium is a TM wave. It is a transverse electromagnetic wave. And we can, I mentioned earlier that you can find the direction of propagation using this cross product. If we define a unit vector in the direction of electric field and unit vector in the direction of magnetic field and a unit vector AK in the direction of propagation, then direction of propagation can be found by simply taking the cross product AE cross AH. So here, let's say in this case, AE is in the AX direction and AH is in the AY direction. You take the cross product AX cross AY, you will get AK in the AZ direction. So this tells you that the wave is propagating in the plus Z direction. Another observation is that electric and magnetic field are in phase. So if you closely observe, both are cosine function, and here phase is 0 and here reference phase is 0. So if in phasor plane, if you draw them, they both lie parallel to each other. So they are in phase. So let's say at some instant of time, if we have magnitude of electric field, then at same instant of time, we also have maximum of this magnetic field. So they are in phase. Electric field maxima and minima, magnetic field maxima are located at the same point. Another observation is that magnetic and electric field magnitude is related. So this was H0. We can find this magnetic field magnitude by simply dividing E0 by this eta. Eta is, we call this intrinsic impedance, it is a constant number which depend on constitutive parameter epsilon and mu. And for free space, it was approximately equal to 377. So, and we also defined the phase velocity u, which was equal to omega by beta. And if you use the definition of beta is equal to omega mu epsilon square root, then u can also be found using the constitutive parameter, that is 1 over mu epsilon square root. And lastly, the wave number of phase constant beta is related by omega mu epsilon square root or 2 pi by lambda. And the wavelength of the signal can be calculated by 2 pi by lambda or u by f. So this is our summary. So let's take one example. I will repeat this example again, but let's quickly go through it so that you can relate these concepts. So this is our electric field in free space. So it's a traveling wave, electric field oriented in the y direction, and the wave is, the first question is find the direction of propagation. क्या होगी जो बताएं? What will be direction of propagation?
Negative x.
Minus x axis. Because we have positive beta x here, so wave is traveling in the minus x axis. Or you can also say that it is minus ax unit vector. This is same equivalent thing. What is the direction of electric field vector in this?
Along y-axis.
Along y-axis, or we say that it is in the ay unit vector. This thing. And let's say I ask you to find the magnetic field h of t using plane wave approximation. Up till now, we in the previous chapter, if I ask you to find magnetic field, then we know that we can use the Maxwell equation. Now, after studying this chapter, we know that under plane wave approximation, we can simply find the magnetic field. So h of t will also be a traveling wave, but it has some unit vector ah, which is not known, and some magnitude h naught. It will be a cosine function, same frequency 10 power 8t plus 2x, and both are in phase. So all we need to do is to find this h naught and ah unit vector. How can we find this h naught? H naught will be
A cross
E
H.
naught by eta. And what is E naught here?
50.
This is 50 and 50, and we are talking about free space. And then eta will become
376.
377. 377 ohm. If you want to use exact value, it is 120 pi. So in this way, you will get the value h naught. What about this ah unit vector? Just intuitively tell me if electric field is in the y direction and direction of propagation is in the x direction.
Z, sir. H, A, Z.
AZ, but we can have positive as well as negative direction. So you can simply tell that it is in the AZ direction. All we need to do is to find in which direction is plus AZ or minus AZ. So we know that AK, AE, and AH, they are all related by this triad. The AE cross AH is, sorry, AK was AE cross AH become AK, and so if we want to find this AH, so all you can do is that AH will be equal to AK cross AE. AH unit vector will be AK cross AE. So in this example, what is AE, AK? Direction of propagation क्या है? Minus AX.
AX minus
Minus AX. And what is AE? Direction of electric field is AY. So if you take this cross product, so AX cross AY will become AZ. So we have minus AZ. So in this way, you can find the direction of propagation. Now we know that the direction of propagation should be in the minus AZ direction. This magnetic field should be oriented in the magnetic field in the minus AZ direction. Please try these two homework where you are given the electric field vector, and please use the plane wave approximation to find the magnetic field. And also, I would like you to go through this example 10.3 and practice exercise 10.3. So this conclude this lecture. Let's रिकॉर्डिंग जो है खत्म करते हैं.